So today, we're going to dive into a fundamental piece of computer code. And we're going to look at a simple, almost common sense fix that didn't just make it a little bit faster, it made it over 300 times faster.
I mean, just think about that for a second. Imagine you're almost done with some huge project. Someone bumps your desk, and poof, you have to tear it all up and start again from page 1. That's the exact frustrating problem we're going to unpack today.
To really get what's going on here, we have to start with the basics. And at the heart of this whole story is a data structure called the linked list.
Honestly, the best way to think about a linked list is, well, it's literally a conga line. Each person is what we call a node, and they're holding some piece of data. But here's the catch. You only know who the person directly in front of you is. That's it. So if you want to get to the 10th person in line, guess what? You've got to walk past the first 9 people to get there. And this is where a really important distinction comes in. A singly linked list is a one-way street. You can only move forward. But a doubly linked list, that's a two-way street. Each person in the conga line also knows who is directly behind them. Now tuck that little detail away because it is absolutely crucial for the solution we're going to see in a bit.
Okay, so a conga line sounds simple enough when it's just one line, right? But what happens when things get chaotic? What happens when you have dozens of different people, or in computer terms, threads, all trying to jump into the line or leave the line at the exact same time?
And that, right there, is the fundamental challenge of what we call concurrent programming. You see, when you have all these different programs, or threads, trying to mess with the same piece of data simultaneously, you get chaos. You could have 2 threads trying to shove a new person into the exact same spot in the conga line, and boom, the whole chain just breaks.
So, how do programmers even begin to manage this mess? Well, they have a special tool in their toolkit, a command called compare and swap, or CAS for short. Think of it as an all-or-nothing operation. It basically lets a thread say, hey, I'm about to make a change, but only if nothing has been touched since I last looked. If the CAS fails, the thread knows, whoops, somebody else beat me to it.
Okay, so this is where things get really interesting, because the standard, by-the-book way of handling one of these failed SAYS operations has a massive, and I mean painfully massive flaw.
You know, the researchers who dug into this problem used a word you almost never see in a serious computer science paper. They called the standard approach draconic. Yeah, like a dragon. Overly harsh, severe, just plain brutal. And here's that painful process in action. Imagine you're a thread. You walk all the way down this long conga line, you finally find your spot, but just as you're about to jump in, someone else moves. Your compare and swap operation fails. And the draconian rule says what? Tough luck. Go all the way back to the very front of the line and start over. You can see how in a really busy system, you could get trapped in this loop forever, never actually getting your work done.
So the researchers looked at this and basically said, this is insane. This full restart is complete overkill. They figured there had to be a much more pragmatic, common-sense way to handle it.
So first, they started with some simple, what they called mild improvements. They said, wait a second, let's actually look at why the operation failed. If someone just slipped a new person in line ahead of you, why on earth would you go all the way back to the start? Just reread the pointer, step over that new person, and keep going from right where you are. So simple, right? But their biggest idea, oh, this is clever. It brings us right back to that doubly linked list we talked about. They gave each thread its own personal cursor, which is basically just a memory of where it last was. And they added those backward-pointing links. So now, if your operation fails, you don't get sent to the front of the conga line. No, you just go back to your friend, your cursor, who's holding your place, and you restart from a spot that's much closer. So, the million-dollar question. Did all this common-sense stuff actually work? Well, let's just say the results were, well, the paper itself calls them dramatic. And they were not kidding. Okay, get this. In a worst-case test, one that was specifically designed to create a ton of these conflicts, the original draconic method took, wait for it, over 162,000 milliseconds to finish its job. The new method, the one with the cursor and the backward pointers, just over 481 milliseconds. I mean, the difference is just staggering. This chart really puts it into perspective. On the left, you've got this giant, towering skyscraper of time for the old method, and on the right, well, the bar for the new method is so tiny you can barely even see it. It's an absolutely incredible improvement. Let's put a hard number on that. We're talking about a speedup of over 338 times. Not 338% faster, 338
times faster. All it took was rethinking that one simple, brutal assumption that you always have to start over from scratch when something goes wrong.
So really, the big takeaway here is this. We spend so much time optimizing for the happy path, right? We focus on making things fast when everything goes perfectly. But this research just proves that being smarter about how our systems recover from failure can unlock these absolutely mind-blowing gains in performance. And that really leaves us with a final question to chew on. Where else in our digital lives are we just putting up with these draconian penalties? What happens when your Wi-Fi blips for just a second during a massive download and the whole thing fails? Or when you fill out a long web form, hit submit, and an error forces you to do it all over again? You start to realize these draconian solutions are probably all around us, just waiting for a smarter, more pragmatic fix.